Hello, my name is Henry Bright. I'm going to be working with Zachary Moore on this final project for Dr. Osbe's Design of Aerospace Experiments class. Um, I will be handling part one while Zachary will be doing part two. So this video will be just regarding part one. And part one is 2D flow simulation over a NACA 2415 airfoil. Um, we're given the free stream velocity of 15 meters per second. And basically our objective is to get the velocity and pressure contours at varying angles of attack, they're specified there, as well as the lift and drag coefficient versus the angle of attack, using the Fluent results, so using the forces and then tabulating the coefficients from there, and doing those at slightly more refined angles of attack. So let's go ahead and get into it. So I'm going to pull up our workbench on Fluent. I went ahead and put in Fluent and open the design modeler to get our geometry. So I'll go ahead and do this start to finish. So the first thing we're going to do is we want to import our airfoil. And in order to do that, we're going to go ahead and create and then point. And we basically are going to import these coordinates from a file. So to show you where we get that file from and what that looks like, if you go to airfoiltools.com, for example, when we pull up this website, we'll be able to search for different airfoils, and they have the coordinate files. So in this case, I'll search for NACA 2415. It's just the one we want, and I should be able to get a coordinate file for that. So yeah, if I go ahead and click on the NACA 2415, there it is, and you can see the data file. So if I open the source stat file, there it is. Now, what you would want to do is copy these coordinates into a new text file, but then you also have to modify it. So I ended up doing it in Excel and then saving it basically as a text file again. So what it's going to look like, let me pull up mine. So let's see. Yes. This is basically going to be structured like this. The columns are a little offset here, but basically what you need to do is you need to add two columns at the beginning, and they're kind of like a source numbering type of thing. I don't have a great explanation for it, but basically it's like this gives you your number of points, like 0.1, 0.2, 0.3. I'm not entirely sure why you have to have the 1 to lead it, but then basically you have your X, you have your Y, and you have your Z, which in this case it's two-dimensional, so Z is 0 for each one. So you basically need these 5 columns, and then Fluent will be able to read it in correctly. So if I go ahead and close out of that, let's go ahead and go back into Fluent. And we'll go ahead and do this. So I'm going to grab that file that I had just shown you. Open. Click there and generate. And now you can see when I zoom in, there is our airfoil. Looks great. So we've got that down. All good to go. So then the next thing we need to do is we need to create, excuse me. Excuse me again. We need to create a 3D curve to basically make the shape of the airfoil to actually connect the points. So that'll be the first thing we do. And then basically we need to select each of these points. So if I go ahead and zoom in, I'm going to start from the trailing edge, actually. Let's see. I need to change this instead of from coordinates file, I need to do point selection. So now we'll be able to select each of the points. And I've tried a box select with this, but it doesn't in the past, but it doesn't seem to work to capture all the points. I think because they need to be in order, which does make sense. You do need to get the points in the order that they are supposed to be occurring so that they can draw the lines properly. So it is a little bit of a tedious process. You do have to click each of these 61 points individually. So bear with me. I just wanted to show this so that there's no confusion. So you know that I somewhat know what I'm doing, and that if you need to replicate, you can as well. So feel free if you want to skip past this part of the video to once I've gotten all of these selected, That would be fine. Okay. Now I finally have all of these selected, so I'll go ahead and hit apply. There we go. We have our 61 points connected, and we'll go ahead and hit generate, create that curve. And it did generate that curve. Let's see if I zoom out, you can see it a little better. Um, so yeah, we've got that. Now the one issue is with this curve is it didn't complete the entire shape. So I don't know if you'll be able to see it because this point is in the way, and I don't know for the life of me how to get rid of this thing. But there's actually a disconnect between this last point at the trailing edge and this other point. So to resolve this, we actually need to um, create another line to complete the curve. And a straight line will be just fine. We'll do exactly what we need it to do. So line from points, if you go to concept and then line from points is what we're going to do. So if I can find, it's almost a guess and check. I can't totally tell where the points are, but if we do that, and then I'll hit control and click the other point, and it's got, you can see it's just barely drawn right there. Very tricky to see, but I believe I got it. So we hit apply and then generate. And now we have our two lines basically completing the surface for the airfoil. So that is good. The next thing we need to do is we need to create a surface sketch. We're going to do a surfaces from edges, so using these edges basically that we've created. And if we click on both this one, and then you can see now much better where that gap was between the lines. Now you can see my lines created as well. So I'll go ahead and hit control and select that one as well. So now it completes the shape. It's a slightly rough approximation, but when you look at how small it is, obviously we're scaled in on a scale of, a couple centimeters. This is definitely like way less than a centimeter, probably like in the scale of millimeters big. So it's not going to make a huge difference. Our chord length here is just the normalized chord length of 1 meter. So pretty small in the context of the whole airfoil, so shouldn't make a huge difference. So we'll go ahead and apply. We have both those edges and generate. And now we've got our little surface for where the airfoil is, which is great. So the next thing we're going to do is we need to create basically our like free stream body. So this is going to be pretty simple. The only caveat to this is we need to have it so that we can vary the angle of attack. So obviously this was a complicated shape to import, and we don't want to have to try and figure out a way to rotate all of these points basically for every angle of attack. So what we can actually do is rotate our surface that we put around it. So we can actually like incline it and whatnot to get the angle of attack that we want. Because our free stream velocity will always be normal to whatever that surface is. So yeah, basically the way we're going to do this is I'm going to go ahead and start by creating a line. Whatever angle, doesn't matter right now. And what I'm going to do is I'm going to reference this with a dimension for an angular dimension. So I actually don't like where this for referencing. I'm going to do this again. And now if I do a dimension and we'll do angle, I'm going to do an angle between this and the x-axis. So I go ahead and create that angle. Now, if I change it to, very strange. Not entirely sure what it's referencing right now. a little bit confused there. Um, okay, there's my, oh, weird. Okay, so this will work. It's a little weird because I'm not entirely sure why it's referencing an angle like this. Um, it's kind of like rotated 360 degrees from where I normally would, but this will be fine. So we'll just deal with this. Um, anyway, so let's go ahead and get some more dimensions on here. For my size, you want basically your kind of like control volume, your free stream volume to be like a good bit larger than your object, just so there's no like blockage effects like you would have in like a wind tunnel or whatnot. So what I did was I think I did 12 meters long. Yep. And then I think I ended up doing 6 meters tall. So I'll go ahead and draw the rest of our lines to complete out like our rectangle here. And then we need to constrain this so that we've got an actual rectangle. Okay, perfect. And then we just need to dimension the height of it. And we'll put it at 6 meters. And that's just an example. I really just chose those numbers somewhat arbitrarily. So you can really do what you want there. And then this is the easiest technique I found for like placing this where I want is I just ended up creating two, let's see, I ended up just placing a vertical and horizontal line in the middle of the rectangle. And I use that for centering purposes to get it approximately centered um, with the airfoil using the like leading edge as my reference. So if I go ahead and do a midpoint constraint and use these center lines, let's say this one. Now you can see at this angle, it's centered about where the airfoil is. So this is great. Um, what I ended up doing in varying these is you do need to delete these lines. So you have to just redo them basically very quick. It's very quick to do, but you could just delete them and then remake them when you need to go to change the angle of attack. But basically then this makes it super easy so that every time you want to run a new angle of attack, you just have to come back into your geometry and change the angle. So in this case, it's 355, which actually just means that it's inclined 5 degrees from the horizontal, which you can see. And this is a positive 5 degrees, not because it's this, but because the airfoil is flat, your free stream velocity is coming this way. So it's essentially like the airfoil, if you were to look at it with the velocity being horizontal, you can see your airfoil is basically inclined upward. So that's a positive 5 degrees angle of attack. So in this case, if I wanted to do like our negative 5 degree angle of attack, I would need to do, let's see, would it be 5 degrees? Yeah, 5 degrees. And you can see now it references it just the opposite. So for example purposes here, I think I'll do our positive 5 degrees. why not? We'll just go with that and we'll see what results we get. But anyway, so yes, I need to delete these references. It still keeps your shape in the right spot, which is nice. And not sure why it's not letting me click on this line. But if I go here, I should be able to delete it. Okay. Now what we need to do is we need to create a surface from sketches. And we'll just box select all of this. So hit apply and generate. And now the last thing we need to do to finish this off so that we're ready is we need to do a Boolean. So we'll go to create and Boolean. And basically what that will do is, because if you look, we have still our surface within our airfoil as well. So we need to change this to a subtract operation. And we'll basically take our target body, which is the general surface, like where our free stream is, because that's what we want. And then we need to subtract out that inner surface where the airfoil is. Apply and then generate. And now you can see we've got basically that hole, so that like our flow will only be in the whole rest of the main surface, but then within the airfoil, we just have our surface fragments. So this looks great. We are done with that. So we'll go back into our workbench and update our geometry. Looks like it may have already updated, but I'm just going to go ahead and click it to make sure. Awesome. So our geometry is done. The next thing we need to do is mesh. And within our meshing, we will also create some named selections so that we can do our velocity inlet and pressure inlet, get like some, or pressure outlet, get some of our like boundary conditions and whatnot. So once that pulls up, we will do that as well. Awesome. So we've got our surface. Lovely. Looking at it in 2 dimensions, we've got that. Okay, so we will click on our mesh, and we're going to go ahead and hit insert, and we want to do method. And the method that I always do is click on the geometry. And the method that I always do is the triangles, all triangles method. You really do what you want, but that's just what I'm familiar with. And then I've changed my element size to 0.003, I believe is what I was doing. Maybe 0.03, I think I was doing. Again, this will just like either get your mesh more refined or less refined. Let's go ahead and try that. Hit generate, and we'll see how that looks. Basically, you just want it to be, you know, pretty finely meshed, especially right around your surface, so that you'll get the best results. But the more you do it, the more processing time and power it's going to take, as well as may not get your solution to converge. So just be cognizant of that. It's definitely something you might have to play around with. There's no, you know, one right answer to it. A lot of times it just depends on the problem you're working on, what exactly you're trying to do. But that's just what I'm doing in this case. So we'll see how that turns out. Oh, sorry. And obviously, this is like a somewhat highly refined mesh, so it takes a little bit of time. Now we've got it. You can see when you zoomed out and it's completely black, that means you've probably got a pretty darn good mesh. Zoom in, you can see very well refined. Looks pretty darn good. I'm happy with that, so we'll go with that. And then the next thing we need to do is we need to do we're going to do an edge selection here, and we're going to create some named selections here. So if we do insert, let's see, is it there? Let me click on the image first. There, create named selection. And we'll do this one is velocity inlet. We'll also label our pressure outlet, which in this case, we're just doing, I guess I'll get to this when we get to the solution, but this will just be 0, like our gauge pressure will just be 0. And then if I hit Control and I get both of these surfaces for our wall, just use wall. And then the last one we need to do is our airfoil as well. Let's see if I can grab the little one as well. Might need to zoom in. Edge. And we'll call that our airfoil. Oh, I don't think I got. I did not get that wall. Okay, let's edit that. It does say 2 edges though. No, I did get it. Okay, it did get it. Okay, it did. Awesome. So we'll go ahead and go into our workbench again and update that. Awesome. So I've got our mesh. Beautiful. So then the next thing will be to go ahead and get to our setup so we can solve. And we'll go ahead and do, I like to double precision with 2 solver processes. Just can help with a little bit quicker calculations, assuming your computer can handle it. Not something you absolutely have to do, but I tend to find it to be helpful. Let's wait for this to pull up. We'll pull our mesh in here, hopefully in just a second. Awesome. And it looks like it's just about done. You can see our mesh over here in the green. Looks like we're good. Yeah. All right. So next thing we need to do, materials should already be loaded. We've got air. That's what we want. And it's air in our cell. So the next thing we need to do is boundary conditions. Well, I suppose there's one more thing. Yeah, so if we go into under models, you can change your flow type. In this case, with the Reynolds number that we were getting, I did calculate the a rough estimate for our like free stream Reynolds number, and it was over. It was into the turbulent phase, I believe. So I used the, I think, K epsilon with enhanced wall treatment. That was just what I did, but you can kind of make your own decision in terms of which method to use or model for your flow. So yeah, I'll just skip past that, but that's what I used. I think, no, I did hit the energy equation. So there's some couple things you can mess with, couple decisions you can make in that regard, but we'll move past that, not super right now. It'll just give you slightly different results. So let's go ahead and go to our boundary conditions. So first off, velocity inlet is the most important. So we need to set that to our 15 meters per second. So we're going to apply, looks good. And then our outlet is our pressure outlet. You can see it's already defined that. I won't have to make any changes here because, like I said, we're just going to do a gauge pressure of 0. So we're good there. And then you've got your 2 walls. You should have both. Yep. So it's got the stationary wall and then wall surface body. So both are going to be the same. There's nothing that we're going to need to change here. But just keep in mind your stationary wall is the one where we did like the two boundaries on the top and bottom surface of like the whole cell. You want stationary wall, no slip condition. It'll be the same for our wall surface body, but that's where our airfoil is. So that's that surface. So should be good there. Methods, again, you can kind of change this to whatever. I think I typically do simple method, least squares, cell based, all the rest of this the same. So again, little things, little details that you can change. But we'll go ahead and initialize this so we can get ready to do our calculations. Looks good. And then running the calculations, I typically do an iterations of 200. It's probably not going to converge, but you'll see a general downward trend in our residuals. So looks pretty good, and it ends up giving us pretty good results. So I will go ahead and run this. We will wait for these calculations to be finished. Okay, looks like we just finished. Awesome, you can see our residuals there, some funky things, but like general downward trends, so doing pretty good. Not gonna worry about it beyond that. But let's go ahead and show you what we need to be obtaining. So the first thing is our contours. So we need both our pressure and velocity contours. We're gonna do our pressure, static pressure. Click on all of these surfaces to get the contour around everything, and go ahead and hit save and display. That. And now if we zoom in, I'll also move this too. So remember that this was for our +5° angle of attack, and it is a cambered airfoil. So even at 0 degrees angle of attack, you're going to start to get some positive lift. But at 5 degrees, we're going to have even more. So you can see this pressure contour makes a good bit of sense. So you can see, pretty high pressure zone here near the stagnation point, and then around the bottom surface, you can see a higher pressure relative to the lower pressure on the top surface, which makes sense because high to low pressure, that's the direction that we want our pressure gradient. You're going to be having that lift force created. So we should have a positive lift force in the end here. So this contour looks really good. So let's go ahead and get our other contour, which is velocity. And we're basically going to be seeing more or less a inverse relationship here. So we're going to hit this. And yeah, you can see, you're getting a much higher velocity going over the top of the surface. You can see again the no slip condition right by the surface on both sides, but you can see we've got a higher velocity now going over, which makes sense. Higher velocity, we're gonna have lower pressure on the top surface. You have the opposite on the bottom surface. Again, we're creating lift. You can see kind of like that stagnation point right there near the leading edge, and you can see just the smallest of wake zones. Maybe even if I zoom out a little bit, you might be able to see it a little more. You can see just like the smallest little wake region where there's a little bit of a reduced velocity in, past the trailing edge of the airfoil. You'll see that really increase at the high angle of attack. When you get to like 20 degrees angle of attack, you'll really see that region. And you'll even see maybe some evidence of flow separation, which is kind of cool. So there's our two contours. Basically, you can take screenshots of that. Very simple. The next thing is we need to get our force reports. So we go into our forces and we want it around our wall surface body. Now the important thing here is our direction vector. So when we are at 0 angle of attack, we would just use this x = 1, y = 0 unit vector would just be for our drag force. And we would just do the opposite, 0 for x and 1 for y for our lift force. But because we have this angled surface compared to, or the angled free stream velocity compared to the airfoil, obviously an angle of attack, we actually need to do some calculations to get a proper unit vector pointing in the right direction to actually get lift. Because if you remember, lift force is always going to be perpendicular to your free stream velocity, and your drag force will be parallel to it. So we need to get a unit vector that is in that proper direction. So if I go back to my spreadsheet and show you this, what I did is I took each of the angles of attack. For this part B, like I said, for part A, for the contours, we just did it for -5 up to 20 at just increasing angle of attack of 5. But for the second part, to get the graph, we wanted a few more data points in there. So I ended up doing just every 2.5 degrees. But anyways, you can see I converted those degrees to radians in this column. And then these next 4 columns, I have the lift coordinates and the drag coordinates for the unit vectors. And they're basically just reversed for each one. So like the X and Y for lift becomes the Y and X for drag. But basically what I did is I just took some, like in this case for lift, in the X direction, you're going to have sine of that angle, and in the Y direction, you're going to have cosine of that angle. So you have mostly close to 1 for most of these for your Y, because your majority of your lift is in that direction. But as you get more and more angled, you're going to have more of it in the X direction. So it's something that you've got to account for. And then, like I said, the opposite basically for drag force. So in this case, we did a positive 5-degree angle of attack. So for our lift coordinate, I'm going to go ahead and copy these in. There's our X value for the unit vector. Go ahead and type that in here, just copy it in. And then we need our Y value as well. So we'll copy that in as well. And now if I go ahead and hit print, you're going to see our force results. So you can see we've got basically our net force is what we would look at. We would use that net force to then calculate the lift coefficient. So you can see at a 5-degree angle of attack, obviously we have positive lift. Makes perfectly good sense. So this is a good result. We got exactly what we were looking for. And then for drag, basically we just switch these coefficients. So I'll go ahead and do that. Just need to go over our Y coordinate here. Let's see. There it is. And print that. And looks like maybe something slightly wrong here. We should be getting a, let's see, what is that? Oh, I think this got copied in incorrectly. Okay, sorry about that. I think my X vector was copied in incorrectly. I should have done that. Let me redo that. Hopefully that'll fix that issue, because that doesn't seem right. There we go. Okay, perfect. So you can see we get a much lower value in terms of magnitude, but we do have a positive value because obviously our drag force is going to be kind of in the direction of our flow. It's a lot less than our lift force, but that makes sense because we're going to get a relatively low lift coefficient since it is a streamlined body, and we'll have a much higher lift force. So these results make perfect sense. So basically you would do this exact same process and just repeat it, go back into your geometry, change your angle of attack to whatever it needs to be, make sure you center it again around that leading edge of your airfoil, and then basically repeat all of these steps. Mesh it again, make sure you get that done, then come in here, and you can basically just initialize and calculate, because if you save all your data for your solver, and then you come in here and just put in, get your contours if you need to, depending on the angle, and then put in your correct direction vector as well, so that you can get the lift and drag force. And then you'll basically be able to get plots, which I can show you what those look like for me, because this is my tabulation, so I got all the forces for each angle of attack for lift and drag, and then coefficients I just calculated by using that formula. So the coefficient equals the force divided by 1/2 rho v squared, v being the free stream velocity. So you can see then I get my coefficients, and then like our lift versus angle of attack graph looks like that, which makes sense. You get kind of like a pretty constant lift curve slope up until you get past like about 5 degrees or so, and then you start to eventually trail off a little bit. You peak, and then you start to go back down, and you start to lose lift once you go past that stall angle, which is probably somewhere in between 15 and 20, probably in between 15 and 17.5, and then we start to go down. And then our drag coefficient versus angle of attack, this also makes sense. As you go to either in positive or negative direction, you're going to get more and more drag because you're going to have pressure drag. You're going to have more of that from it being more and more like a blown body. So you can see this trend makes very good sense. So that's a good summary of my results. That is how you solve this project for part 1. So thank you for listening.